All right, now that you're finished assignment 6F2, this is what you'll see in class. Very similar. The only new thing is that you have to remember what the inverse of sine is, or inverse of cosine, or inverse of tangent, or inverse of all of those things. And what is it? It looks like this: sine to the -1s. That means inverse of sine. That means you can put a ratio here and then hit enter on your calculator, and it will give you a degree measure or a radian measure. You're not going to need that a whole lot here in this next section, but I think depending on the problems, you might towards the end. This is section 6.71, graphs of transformed sine and cosine functions, day 1. So this is the big deal section that's going to be most applicable to your final exam project. We've been dealing with transformations, vertical shift, horizontal dilations, and all that stuff ever since we learned about functions, and now it's time we apply that to trig functions too. So let's do just a little quick reminder. Here, let's do the for the next couple of graphs, we're going to do the function f of x is equal to x to the 4th minus 16x squared, just so you can see what it looks like. So here's the blue, and if you do a vertical shift of plus 20, then it would look like this. You've got the d value on the outside right here, on the outside of the function, adding 20. Here, a vertical dilation, it will stretch it or compress it or even flip it in this case. So a vertical dilation of -1 would look like that. That means that the c value is equal to -1. And it's on the outside being multiplied. Horizontal shift. So we have, it'll look like this. If you go from this graph to this graph, it'll be a horizontal shift of plus 5. And you notice that in the equation, it would have to be f of x, like x minus 5. You know that we have to take the opposite of what we see here on the inside of the function. It's got to be added or subtracted. I know that when my students often see this, they say, well, you have to take the opposite of what you see. So minus 5 becomes plus 5. And that's true. It's not false, but I want to offer a second way of thinking about it. A second way of thinking about it would be that you have to force subtraction. If you see addition, f of x plus 2, then you have to force subtraction, f of x minus what? It would be the opposite of positive 2, which is negative 2. F of x minus negative 2 is the same thing here. We know that because the two negatives could cancel out and you go back to the original. But I think one of the benefits of thinking about it this way is that you've got a formula, x minus a, and so you can look here at the formula and see what the horizontal shift would be. In x minus what? It's x minus -2, and that's why it's a horizontal shift of -2. It has a particular strength in thinking about it like that because we can also apply it to horizontal dilations, which we haven't touched a whole lot, but we're going to start doing quite a few with trig. We haven't done a whole lot of horizontal dilations because the same effect on the graph can be achieved with a vertical dilation often. So, but that's not exactly true of this graph. You can see we've got a f of x divided by 2. That's a horizontal dilation of 2. It's twice as wide. All the x values get multiplied by 2. So this has like an x value of, I don't know, like 3 or something, and it gets doubled to 6. Here's -3 gets doubled to -6. Here, horizontal the x value is 0, so it gets doubled to 0 and stays right here. All these x values get multiplied by 2 because it's a horizontal dilation of 2. Now, the formula is f of x divided by b. So just like you were able to force subtraction over here to find out the horizontal shift, you can force division. Let me show you what that means, what that looks like. When you force division, like here I see multiplication. If you wanted to force division, you could take its reciprocal. So f of 3x is equal to f of, I know this is a fraction within a fraction, but it helps us figure out what the horizontal dilation is. It's x divided by 1/3, which is the same thing as multiplying by 3. But you can look at this and just read right off the equation, what is the horizontal dilation? It's 1/3. Again, the reciprocal of -5 is -1/5. So f of x over negative 1/5 is negative 1/5. The horizontal dilation is negative 1/5. Here the reciprocal of 1/2 is 2. We see multiplication here, but we can force division by putting the x in the numerator. 1 times x is x, so it's just x over 2. It's also the reciprocal of 1/2, 2. All right, now that we know that, we are able to sketch graphs a lot more easily. So check this out. I'm gonna do the same sine graph a couple different ways, and I'm gonna make the same table. Remember, this is a really great method for keeping track of your work and organizing it all. So from memory, we should be able to sketch out this graph here. And if it's not from memory, then it should be soon. That's something you should work on. We know that the sine graph starts at 0, 0, goes up, it goes down, it goes, and then it returns back to the original at 2 pi. Same thing here. You go from 0 to negative 2 pi, one full cycle. And so then the table values of those, and I'll just do the positive ones. Table values are 0, 0, pi over 2 goes up to 1, pi goes up to 0, 3 pi over 2 goes to negative 1 down here, and then 2 pi is back to 0. I'm just going to do these values here, not the values that come from 30, 60, 90 triangles, but the values that, or even 45, 45, 90 triangles. I'm just going to pick these 5 values. I'm going to do the same. They'll start with the same table for all these examples, and that way it'll be a bit more consistent. And even more than that, I'm going to focus in on this row, the second row each time, and it's going to be highlighted here and highlighted here. Although I could explain multiple rows. I think just for the video we'll do that. Anyway, when we have a vertical shift of 3, we know we have to add 3 to all the y values. So from this table, this is an xy table of values for the sine function, but if you wanted to then furthermore add 3 to the y values, you just take all these numbers and add 3. So a height of 1 becomes a new height of 4, and the whole thing gets shifted up 3 units. That's what it looks like. It's 3 units higher. Here's the same thing when it's y equals 2 times sine of x. That's a vertical dilation of 2. I know I need to multiply all the y values by 2. So here's the same table again in the same row highlighted. You can see now the heights get twice as far away from the x-axis. All the positive values get more positive, all the negative values get more negative. And all the 0 values stay at 0. You can see they intersect each other. These two graphs, the parent and the transformed, they intersect at these points where they touch in the x-axis, because 0 times 2 is 0. Next example. Sketch a graph of y equals sine of 2x. Now here's where we have to force division. Take the reciprocal of 2, put it in the denominator. X divided by 1/2 is the same thing as 2x. So we can see very quickly it's a horizontal dilation of 1/2. Once you're able to force division, you get the horizontal dilation very easily. Horizontal dilation of 1/2. So here's the same xy table. It's highlighted in gray. You can see here, and then I'm going to multiply all these values by 1/2. 0 times 1/2 is 0. Pi over 2 times 1/2 is pi over 4. Pi times 1/2 is pi over 2, and you can see how it goes. So all of these x values got multiplied by 1/2, and therefore they all get compressed horizontally. They all get closer to the y-axis by a factor of 1/2. So it's really helpful to sketch out the original, the parent function, and then you can make sure that it gets it's just half as wide. Sketch a graph of y equals sine of x minus pi over 2. Remember, we have already had subtraction forced for us. That's fine. So we can see it's a horizontal shift of pi over 2. So that's going to be a change to all these x values. So you can add pi over 2 to all of these. 0 plus pi over 2 is pi over 2. Pi over 2 plus itself is pi. 1 pi plus pi over 2 is 3 pi over 2. and all of these, and you can see so forth. The y values remain unchanged. So therefore, it's going to be a horizontal shift of pi over 2, and it's going to look like this, from here to here. So some terminology. We've talked about horizontal shifts and vertical dilations and horizontal dilations before, but when you talk about it specifically with trig functions, then you can say that the horizontal shift is what most people call just the phase shift. That's trig function only, or periodic functions only. The absolute value of the vertical dilation is the amplitude. We've seen that before. It's just an easier way to talk about it now. Period is going to be, here's a formula for the period. Period is equal to the horizontal dilation times 2 pi. It's the b value. So if you want to know what the period is, so here are two different things, and if you know either one of them, you can get the other. Like if you know the b value, you can get the period. If you know the period, you can get the b value by putting them into this formula. Now, we've never really had this before. Maybe in a couple of challenge problems, we've never had a horizontal shift and a horizontal dilation at the same time. So before we do that, because it's going to be a little complicated, I'm just going to go to my happy place and tell you about the Channel Islands. In California, one of the most beautiful places I've seen are just, the Channel Islands. They're not exactly pristine, but because there's lots of like human settlements there, but it's a place you can only reach by either plane or boat, and it's a really wonderful national park. I highly recommend it if you ever get the chance. Okay, now that I've been to my happy place, let's forcibly factor this. So sketch a graph of y equals sine of 2x minus pi. We've got both some sort of a horizontal shift and a horizontal dilation going on. And the only way to read this off the graph is to put it in a fraction like this. Let me show you what to do. If you see a coefficient on x, you can factor that out. So never mind that there's no, like, you can't divide pi over 2. Let's forcibly factor. If you factor out a 2, if you put parentheses and factor out a 2, then you have to ask yourself, what times 2 would give you pi? Well, I guess it's going to have to be pi over 2. So therefore, we've got this, and now because we've got multiplication here, we can take its reciprocal and put it in the denominator of a fraction. Once we have x minus a number divided by a number, you can read off of the equation what the horizontal shift and horizontal dilation is. There's a horizontal shift is going to be pi over 2, that's here, and the horizontal dilation is 1/2. The a value is pi over 2, and the b value is 1/2. So let's make it a happy table. Now, order matters on this thing. You're going to do both operations on x and y. So, both operations on just x. So you have to make sure you do them in the right order. You can't add first and then multiply. You've got to do the PEMDAS, first multiply and then add. I will also say that if you do a lot of these transformations all on top, like here, the a, b, c, d values will line up in alphabetical order. So a comes first when you're reading the table left to right. Anyway, you can start off with the original sine function that we have, and then you can multiply all these values by 1/2, like pi over 2 times 1/2 becomes pi over 4. And then when you add pi over 2, you get, this is 1 pi over 4, and then you add 2 more pi over 4, you get 3 pi over 4. That might be something that you should do on the side. If fractions are giving you difficulty, then it'd be good to write out on the side. However, keeping track of all the coordinates is really good on this table. So here you can see that two things are going on with this graph. If you plot all these points, this last x that you find here, not the middle x's, but this one all the way on the left-hand side, and these y values, you can see that the y values are not affected at all. They're still all the same heights. But two things are going on. First, we're dilating it by 1/2. You can see here it's narrower, it's less wide, and then it's also shifted to the right by pi over 2. So plotting these points will put you right where you need to be. And actually what I did was when I sketched this, I don't know if you can see it, there's a little dot here. I put a dot here, a dot here, a dot here, a dot here. These are all dots, and then I was able to connect. I made the dots from the table, and then I connected them with kind of like half circles going the way. Your sketch doesn't have to be this beautiful. I know it is quite a work of art, but this is what we're going for right here. Okay, let's do another example. Wow, there's a lot going on. We've got 3 different transformations. We've got a number out here. That's going to be the vertical dilation. That's the C. We've got and then we've got a whole bunch of junk in the middle we've got to clean up. So we've got to forcibly factor. I don't care what this number is. Let's factor out a 2. Inserting parentheses, we got 2 times x. And then you have to ask yourself, what times pi over... what 2 times what would give you pi over 2? Well, that would be pi over 4. Because when you distribute the 2 to the x, you get 2x, and you distribute the 2 to the pi over 4, you get pi over 2. Then, taking the reciprocal of 2, you put it down here in the denominator. And maybe we should even forcibly take subtraction also. Change this to a negative pi over 4. That way we can read it off the graph. The horizontal shift is going to be negative pi over 4. That's the a value. The horizontal dilation is going to be 1/2. That's the b value. And the vertical dilation is 3. That's the c value. So we have to do the a and b get operated on x, and the c gets operated on y. Let's do the c first. If you multiply all these values by 3, you get these values. You have to first multiply, and then you have to add or subtract. So then we get b times all these values times 1/2, and then you add negative pi over 4, and you get these values here. So you don't have to plot the middle 3 columns. You only have to plot these x's and these y's as points. Here's the original that you can sketch. I hope you can sketch these by memory now. But here are the points. We've got point here, point here, point here, point here. And then I'm connecting all of these with the arcs. Notice pi over 2 got multiplied by 1/2 to get pi over 4, and then I added negative pi over 4 to get 0. So the x value is 0 and the y value is 3. That's why it got all the way up here. It went from here, got transformed from here to up here. There's a lot going on in this. First, let's clean up the inside so we can forcibly factor. So 2 pi times x, so that the reciprocal of that is going to be 1 over 2 pi. That's going to be a really crazy horizontal dilation to think about. But actually, the end result is that it cleans up the numbers. The numbers are actually very easy to graph when you have a pi as a coefficient. The vertical dilation is 3. The vertical shift is -1. Those are b, c, and d values. B, c, d values. We do the multiplication first, and then the subtraction. So multiply all these y values by 3, and then subtract. You get that. Multiplying these x values by 1 over 2 pi, first of all, I just want to say that all the pi's are going to cancel out. You get a pi, and then all these pi's are in the numerator, and all these pi's are in the denominator, so they cancel out completely. So it's basically like 1/2 times 1/2 is 1/4. 1 times 1/2 is 1/2. 3/2 times 1/2 is 3/4. You get the idea. Looking at this row, the row that we've been focusing on, I'm not even going to sketch the original because it's a lot easier to label these. So far we've been, like before, we labeled these tick marks by increments of pi or half pi or whatever. But now, because we have to plot the points that have these just like rational, very easy to think about fractions, it's a lot easier to just do those tick marks and ignore the original sketch, because the sketch would not fall up, it would not line up with these tick marks. So here is this row, 1/4. You go over 1/4 and up 2, it's a kind of it's not a square scale at all. This is the value of 1 on the x-axis, and this is the value of 1 on the y-axis. But I did that so that it would be a little easier to sketch. I wanted to go from a low of -1 up to a high of -4, and from 0 to 1 is here, and it just repeats as well. Now, here's the mother of all transformations. From day one that I've taught you transformations, I've been thinking about this example and how to best teach it so that you can organize your work in a way that makes sense. And you can, like, I'm not joking at all. I really have been thinking about this example for months, ever since I made that first video. And now we get to cleanly organize everything in such a way that minimizes the difficulty, confusion of doing something that has 4 transformations on it. Parent function is sine function. Let's clean up the inside. Forcibly factor out a pi. I don't know if in your handout you have a pi right here, but if you don't, make sure you add it in. What I want to do is I want to sketch a graph of something that has pi x minus 3 pi. Forcibly factor out a pi. Look at that. We get pi times parentheses x minus 3 because you factored out the pi. The reciprocal of that would be 1 over pi. And although it looks ugly now, it's going to make for happy x values later. Just so now that we have it in this form, we can look at the equation and find our a, b, c, and d values. The a value is 3 because it's x minus a positive 3. The b value is 1 over pi. The c value is 3. The d value is 2. A, b, c, d. This table right here is the original sine function, like the original sine of 0 is 0, sine of pi over 2 is 1. But you can do your c values, multiply first and add. So, for example, pi over 2 turns, it's like the y value is 1, so you multiply by 3 and add 2. You can multiply by 3 and add 2 here. I want you to actually multiply by 3 to get this number here and then add 2 to get the number that you'd have to graph, the y value. And then you have to do the multiplication first and then also the addition. So multiply these x values by 1 over pi, which is actually super easy to do. You just know that the pi's are all going to cancel out and you're left with the original fractions. And then you're going to add 3 to all these fractions, which is not too bad. Plot the points. These x, nothing in the middle, only this x and this y. And this is the graph that you get. If you plot the points, the 1, 2, 3, 4, 5 are these 5 dots, 1, 2, 3, 4, 5, and you can continue in the same direction backwards also for two different periods. For example, 3.5 and 5 is this point right here. 3.5, 5. Wow, that's a lot. So you can copy the problem list, start 6F2, and I will see you in class.